Hello, my name is Magnus Petersen. This is my tutorial number 12 on TensorFlow, and this is about adversarial noise for the MNIST dataset. This builds on the previous tutorial number 11, but I recommend that you also see this tutorial because it has a lot of interesting things. In the previous tutorial, we found specialized noise for individual images, which made the inception model misclassify that particular image. In this tutorial, we're going to find a single noise pattern, which is going to make a convolutional neural network misclassify almost all input images. We are also going to try to make the neural network immune towards adversarial noise, and we're also going to show how to do the optimization completely in TensorFlow, whereas in the previous tutorial we used NumPy for optimizing the adversarial noise. This flowchart shows approximately what we're going to do. We're going to take an input image, in this case it shows the digit 7, and we're going to add the adversarial noise. This is the same noise for all the input images. The red noise pixels are positive values and the blue pixels are negative values. So when we add this to the input image, we get something like this, where the red pixels in the noise have made the input image slightly darker, and the blue pixels in the noise have made the input image slightly brighter, although this is difficult to see in this particular image. Then we send the noisy image to the first convolutional layer and the second convolutional layer, then we flatten it and we send it through a fully connected layer, and then we have another fully connected layer which is a part of the softmax and loss function. So we have the softmax classifier here, and it gives the predicted class 3 because we have added this adversarial noise to the input image. The loss function is the usual cross entropy, and we have two optimization procedures. The first one is the normal one, where we're trying to make the neural network good at classifying the input images. In this case, we use a true class number for the loss function, and in this case it's a 7. And then we take the gradient of the loss function with regard to all the variables in the network, and then we update all the variables, like so. The second optimization procedure is trying to find the adversarial noise. Here we have locked all the variables in the neural network so they will not be updated during the optimization, and we only want to update the adversarial noise over here. We use the same loss function, but we instead input the adversarial class instead of the true class. So in this case, let's say we want all input images to be misclassified to the target class 3. So we input the number 3 to the loss function. We also have what is called an L2 loss, and I may have mentioned this in one of the earlier tutorials, but what it does is that it tries to minimize the noise. So we have two loss functions, cross entropy and L2, and the cross entropy tries to maximize the classification accuracy, and the L2 loss tries to minimize the amount of noise. And we add them together and we have the combined loss, and we use the gradient of this combined loss to update the adversarial noise. So there are two optimization procedures, one for making the neural network good at classifying the input images, and one for optimizing the adversarial noise. As usual, we have imports, and we have to load the MNIST dataset, and we have a helper function for plotting the images. And we can plot a few examples just to see that we have loaded the data correctly. We have a 7 and a 2 and a 1 and so on. So now let's build the TensorFlow computational graph. And this is quite similar to what we have done in previous tutorials, where we have made a convolutional neural network using PrettyTensor. But now we will also add the adversarial noise, and we will also need the extra optimization procedure for that noise. So as usual, we have a placeholder variable that we call x, and this is for taking the image input to the neural network. And because these are flattened arrays for the MNIST dataset, we just have to reshape it into an image size. And then we have a placeholder variable for the true class as a one-hot encoded label. Now we want to add the adversarial noise. So first we have two constants that control the level of the noise and how it influences the L2 loss function. So we set the noise limit to 0.35. And this means that we allow the noise to be either positive 0.35 or negative 0.35. All the pixels in the input image are floating point values between 0 and 1. So we allow the noise to either add or subtract about a third of the intensity range of a single pixel. And remember that the L2 loss tries to minimize the level of the noise. And when we are adding this L2 loss to the normal loss function, we typically scale it down to almost 0 because that works best. So here we have the weight for the L2 loss, and we set that to 0.02. And in the exercises, I suggest that you try and change these two numbers and see how it affects everything else that we're going to do below. And now we want to make the TensorFlow variable for the adversarial noise, but we don't want that variable to be optimized along with the rest of the neural network. So we need to use something called variable collections in TensorFlow. So what we do is we give a name to our new collection for adversary variables, and it is just a string like this. And then we have a list of the collections that we want our new noise variable to belong to. And this is a bit confusing, but if we add it to graph keys.variables, then the noise variable will also be initialized with all the other variables in the graph, but it will not necessarily be optimized. And we will see why in the next line. And we also add the new noise variable to our new collection of adversary variables. So this is where we define the TensorFlow variable for our adversarial noise, and we want it to be initialized with 0 values in this shape. So this is the shape of an image, and we give it a name so that we can find it again. And then we say here, this is important, trainable equals false. And this means that this variable will not be optimized along with the rest of the neural network. We will create our own separate optimization procedure for that. And then we say that we want the variable to be added to the two collections up here, our adversary variables and the graph keys.variables, so all the variables in the graph. Once we have updated the noise further below, we also want to clip it or limit it to the noise limits that we have set above. And this will not be executed at this point in the computational graph, but it is something that we will execute after we have done each optimization step for the noise. And this might be a little confusing, but I think it will make sense when we get further down in the source code. And then we create the noisy image simply by adding the input image and the noise. We also have to clip the noisy image, so all the pixel values are between 0 and 1, so the noisy image is a valid image. And then we get to the point where we make the convolutional neural network, and we're going to use pretty tensor for this. So as usual, we wrap the input tensor, which in this case is X noisy image, and then we get a pretty tensor object out, and we can use this pretty tensor object to construct our neural network simply by calling functions on it, like so. And this creates the neural network that you saw in the flowchart above. And what we get out is ypred and the loss function. So we have the predicted class and the loss function for optimizing this neural network. So let's take a look at all the trainable variables for the TensorFlow graph. And we get a list like this. And what you see here is that x_noise is not in the list. So when we create an optimizer for the neural network, it will not optimize x_noise, that is our adversarial noise. So we set the optimizer for the neural network like this, and we use the ADAM optimizer as usual because it seems to work fine. And we set it to minimize the loss function from the neural network. So let's have a look at the flowchart again. What we have just created is this neural network here with all the convolutional layers and fully connected layers and so on. And what we get out here is y_pred, and we have the loss function here, and we have the optimizer up here, which is the ADAM optimizer that updates all the variables in the neural network. And now we want to create the second optimizer for the adversarial noise. So first we get the list of variables that we want to optimize. So we get the variables in the collection that we defined above. And there's only one variable in that collection, and it is x_noise. And then we create the L2 loss function for that noise, and we scale it by the weight. And then we combine the normal loss with the L2 loss. And we create another optimizer, which minimizes this combined loss. And once again, we use the ADAM optimizer, but this time we have a much higher learning rate, which seems to work well. And we instruct the optimizer to use the combined loss function and only to optimize the list of adversarial variables, which was just x_noise. So if we look at the flowchart again, what we have created now is the L2 loss here and the combined loss. This is the optimizer here, which will update the adversarial noise using the gradient for the combined loss function. And one of the great things about TensorFlow is that these gradients for the loss functions are computed automatically by the TensorFlow framework, because the network is just a combination of basic mathematical functions, and TensorFlow then uses the so-called chain rule of differentiation to find the gradient. So now we have created this whole neural network and the two separate optimization procedures for the neural network and for the adversarial noise. So before we can run this computational graph, we first need to create a TensorFlow session, and then we initialize all the variables of the graph. And we will make a little helper function for initializing the noise variable as well, because we might want to call this several times. And then we have a helper function for performing the optimization iterations. And it looks like this. And it is very similar to the previous tutorials, except that now we have the adversary target class as an argument to the function. And if this target class is set to some integer, then we will fake the class labels so they become this target class. And when we run the optimizer, we use the adversarial optimizer instead. And we also have to execute the noise clipping, which I showed you above, and which makes sure that the noise after it has been updated by the optimizer is limited to the range that we have set. And the reason we cannot execute this in the same session run as the optimizer is that the session will try and parallelize this code, so we are not guaranteed that the execution order is what we want. And first we want to execute the optimizer, which will update the adversarial noise, and once it has been updated, we want to clip it or limit it. So these are all the changes that we have made to this function for doing the optimization. Then we have a helper function for getting the noise from the TensorFlow graph, and it is very simple. And here we have another helper function for plotting the noise and printing some statistics. Here's a helper function for plotting some examples of images that have been misclassified. And the only difference from the previous tutorials is that we have to get the noise and we have to add that to the images before we plot them. And here's another helper function for plotting the confusion matrix, and another helper function for plotting some classification accuracy and various other things. And this is exactly the same as some of the previous tutorials. So now let's start experimenting with this. So first we're going to run the optimization for 1000 iterations. And let me show you on the flowchart what it does. At first the adversarial noise here is 0, so it's just white. It doesn't have any effect at all. And we're going to feed thousands of different images from the training set into the neural network. And we're going to use this loss function here with a true class for each of these images. And then we're going to use the ADAM optimizer to update all the variables of the neural network so that over time it becomes pretty good at classifying the clean input images from the training set. And if we go back, we see that after 1000 optimization iterations, the classification accuracy on the test set is 96.4%. And here we have some examples of images that were misclassified. So this is supposed to be a 4, but the network predicted that it was a 6. This is a 9. It was predicted to be a 7. This is a 3. It was predicted to be an 8, and so forth. Now we want to find the adversarial noise, and we start by initializing the noise. And we already did this above, but in case you want to rerun this Python notebook, you may want to do this again. And now we run the optimization helper function, but we set an adversary target class to 3. So let's go back to the flowchart once again. And what this means is that we set the adversarial class 3 to here, and then we ignore all the variables in the neural network, and we only want to optimize the variable for the adversarial noise. So we are using the gradient of the combined loss function here to update the adversarial noise over here. So we take an input image and feed it all the way through the neural network. We calculate the loss function with the adversarial class. We calculate the L2 loss function for the noise, and we add those two loss functions, calculate the gradient of that, and we update the adversarial noise. And we continue doing this for thousands of input images until we have found the noise pattern that causes all the input images to be misclassified as our adversarial class, which we have set to 3. So whether this is a 4 or a 9 or whatever the image might show, we want it to be classified as 3. And when we have run that adversarial optimization for 1000 iterations, we get this noise as output. So remember that the red pixels are positive values and the blue pixels are negative values. So the red pixels make the input image darker in those areas, and the blue pixels make the input image lighter. And when we add this adversarial noise to all the images in the test set, we get a classification accuracy of about 12%. And here's an example of an image that has been misclassified. So it's a 7, but it is misclassified as a 3. And this is really a 2 that has been classified as a 3. And this is a 1 and a 0 and a 4 and a 1 and so on. And they have all been misclassified as a 3, which was our adversarial target class. And we can also take a look at the confusion matrix, which shows that almost all the images are now misclassified as a 3. 0, 1, 2, 3. So if we look at the flowchart again, we have the exact same neural network that got a classification accuracy on the test set of about 96%, and we haven't changed any of the variables for that network. The only thing we have changed now is that we have changed this noise pattern down here, so that when we add this noise to all of the images in the test set, suddenly the neural network can no longer classify the images, even though a human can easily see. We can see the noise, but we can also easily identify which digit the image shows. So let's try and find the adversarial noise for all target classes. So for each of the classes between 0 and 9, we want to find the adversarial noise that causes the neural network to misclassify all the input images to that specific target class. So we basically just have a for loop where we go through each of these class numbers, and then we save the adversarial noise for later. And to make this run faster, I have limited the number of iterations to 300. And in most cases, it's sufficient, except for this target class of 1, where it is having problems finding the adversarial noise, and perhaps you want to rerun this with more optimization iterations. And then we can plot the adversarial noise for each of the target classes. So here it is for target class 0, 1, 2, 3, and so on. And in some of these, you can see traces of the shapes of the numbers of the target class. For example, this one, you can see the shape of a 0. And this one, you can sort of see the shape of a 3. But the others are more difficult. So we have now seen that we can create adversarial noise that makes our neural network misclassify almost all input images to whatever target class that we want. And these are just single noise patterns for each target class. So you don't have to find the noise pattern for each individual input image. You just have to find it for each of the target classes. So this is a huge difference from what we did in the previous tutorial, where we had to find the adversarial noise for each individual input image. Now let's see if we can make the neural network immune to adversarial noise. And the idea is that we first find the adversarial noise, and then we retrain the neural network so that it learns to ignore this adversarial noise. So if we look at the flowchart once again, what we're doing is we find this noise pattern here, and then we run another optimization for the neural network so that we fine-tune all the variables of the neural network itself to ignore this noise pattern. So let's see how that works. So first we find the adversarial noise, and this gives us a classification accuracy of the test set of 12.4%. So the noise causes the network to misclassify almost all of the input images to the target class 3. And then we run the optimization for the variables of the neural network so they are fine-tuned to ignore this noise. And then the classification accuracy on the test set is back up to 95.4%. So the neural network has learned to ignore the adversarial noise. But maybe we can find another pattern of adversarial noise that can now fool the updated neural network. So let's try and run the helper function for making the network immune again. So first we try to find adversarial noise for the supposedly immune network, but this doesn't work so well anymore. Before we could find adversarial noise that made the network misclassify almost all input images, but now it still has a classification accuracy of about 77% on the test set. So the adversarial noise doesn't work so well anymore because it seems the neural network has now become more robust towards adversarial noise, and we can run another few hundred optimization iterations to fine-tune the neural network again, and then we get a classification accuracy of 95% on the test set again. And you can try and run this make immune procedure several times and see if the network becomes more and more robust. But let's now try and make the neural network immune to adversarial noise for all target classes. So we just loop through all the target classes and call the helper function for making the network immune. So what we see here is a somewhat similar pattern that if we have the target class 0, we are able to find adversarial noise that causes the network to misclassify a lot of the input images. And then we can fine-tune the neural network so that it learns to ignore that adversarial noise, and once again gets a high classification accuracy on the test set. And this goes again for the other target classes. And it would seem that maybe the network becomes more and more immune because after we find the adversarial noise, the classification accuracy on the test set is not that bad. For the target class 2, even when we have optimized the adversarial noise, it still gets a classification accuracy of 52%. But here for the target class 4, we are actually able to find adversarial noise that gives a classification accuracy of about 16% on the test set. So this misclassifies almost all input images. So it seems that we can't make the neural network immune to adversarial noise for all the target classes using this method. What we can try instead is to make double runs of the makeImmune helper function, because this seemed to work better when we did it above. So let's take a look. Here we have the target class 0, and in the first run, the adversarial noise is somewhat successful because it causes the neural network to misclassify more than half of the input images. But in the second run, we can no longer find adversarial noise that makes it misclassify the input images, because the neural network has now become immune to adversarial noise for that particular target class. And this seems to be the same for the other target classes. So here we have target class 1, and at first we can create adversarial noise that causes misclassification for more than half of the input images, but we can make the neural network immune to adversarial noise for this target class again, like so. But for the target class 7, we can actually find adversarial noise that causes the neural network to misclassify about 80% of the input images. So even though the neural network was immune to adversarial noise for the other target classes, it is not immune for the target class 7. So it seems that we cannot make the neural network immune to adversarial noise for all the target classes simultaneously, at least not using this method here. And maybe you can come up with a modification for the method that would make the neural network immune to all target class at the same time. So let's try and plot the adversarial noise that we have found through all these many optimization runs above. And it looks like this. So we have some positive noise values in this area here in the middle and out near the edges here. And then we have a huge blue circle here, which are negative noise values. So let's see how well our neural network is performing now when we are using this adversarial noise over the input images. And now we have a classification accuracy of 97.7% on the test set. And note that this is actually higher than the accuracy we had on the clean images when we had just trained the neural network once. And these are some examples of misclassified images. So this is supposed to be a 5. It was predicted as a 6. And this is kind of hard to tell because the 5 is not written very well. And this is a 6, which was predicted as a 0. And we can sort of understand why it makes this mistake. And this is an 8, which has been misclassified as a 4, and so on. So now let's see how the neural network performs on clean input images. So we set the adversarial noise to 0 by calling this function. And then we calculate the classification accuracy, which is about 91%. So the neural network has been fine-tuned to ignore adversarial noise, but now it doesn't perform so well on clean input images anymore. And these are some examples of images that have been misclassified. So for example, this 9 has been classified as a 4. We could make the neural network immune to one target class at a time, but apparently not to all the target classes at the same time. And one suggestion that you could try out is to interleave the immunity training for the different target classes instead of doing a full optimization for each target class in turn. And you should be able to do this with only minor modifications of the source code in this notebook. Another suggestion would be to have 2 tiers of neural networks, so that we would have 11 networks in total. The first network is not trained to ignore adversarial noise, so an adversary could still fool the first network, but we would use the predicted class of the first network to select one of the other 10 networks in the second tier, and each of those networks have been made immune for that specific target class. So an adversary could fool the first network in the first tier, but he could not fool the network in the second tier because that has been made immune to that target class. And this might actually work, but if we have a very large number of classes, then we would need the same number of neural networks. And for example, the ImageNet dataset has 1,000 different classes, and the inception model is very large and takes a very long time to train. So it is not feasible for all problems, but it might work for the MNIST dataset, and you could try that out as well. I have also made some suggestions for other exercises, and I think you should try and go through most of these if you can. Some of them are easier than others, but it will make you better at using TensorFlow if you try and solve them. And you can download all the source code by clicking on the link below the video.